In this lesson, we will learn how temperature affects a reaction at equilibrium. So first of all, we learned how pressure and concentration affects a system at equilibrium, but K equilibrium is still the same. Okay, K equilibrium is a ratio of products over reactants. In the end, no matter how much A and B and C you have in the beginning, in the end you'll have the same ratio as K equilibrium ratio. The same thing with pressure. Temperature, though, is the only factor that will change K equilibrium. That's something that you should know. First, equilibrium constant will change. Now, what happens to equilibrium if you change the temperature? What you're going to do is you're going to treat heat as if it were a reagent. Okay? If the system is endothermic, that means you're putting heat into the system, then you're going to make heat a reactant. If it's exothermic, that means it was produced. That means you're going to treat heat as a product. Let me demonstrate. Here it says this is an exothermic reaction, which means heat exits, which means it's produced on this side. So heat is one of the products. These are the products, and these are the reactants. Therefore, if you add heat is in the product side, is going to go to the left. Okay? And if you take away the heat, it needs to be replaced, so it's going to go to the right to fill it back up. Okay? Let's go ahead and see what happens to K equilibrium. Let's do the first one again. Add heat. Remember, K equilibrium is equal to products over reactants. Okay? If you add heat's on the product side, is going to go to the left. What you're going to do is the number of products will go down because you're going left, you're going backwards, and the number of reactants will go up because you're going to the left. You're going to have more of this, which means if this R number goes up, K equilibrium will have to go down, so it'll decrease. Okay, pause the video and do the next one, number 2. Okay, so let's take away the heat. If you take away the heat, you're going to the right, which means K equilibrium is equal to products over reactants. If you go to the right, you're going to make more products, so the number of products will go up. So if the products go up, that means your K will also go up. Okay? So if you're a scientist and you really want to make some ammonia, what would you do? Would you make your factory environment hot or cold to make more products? Of course, you would make it cold. As you make the heat, you take it out, so it keeps going to the right. It keeps filling it back in. As it fills back in, you're also going to make more ammonia. You're going to make more product if you're taking away the heat, and your K equilibrium increases. Okay, let's go ahead and try the endothermic one. You try this yourself. Pause the video, please. Okay, this system is endothermic, which means heat is right here. I'm going to write heat here. So if you add heat, it's going to the right. If you go to the right, you make more products. If you make more products, K goes up. If you take away the heat, it's going to go backwards to the left to fill it back up. If you go backwards, you're going to get less products, and the K will go down. Okay, let's try this problem. Using LeChatelier's principle to predict shifts in equilibrium. Consider the equilibrium N2O4 goes to 2NO2. In which direction will the equilibrium shift when A, you add this? Go ahead and pause the video and do the entire thing and see if we get the same thing. Okay, so if you add N2O4, it's going to go to the right. Letter B. If you remove NO2, take this away, it's going to fill it back up, so it's still to the right. C, the total pressure is increased by adding N2. Since N2 is not a part of the reaction, nothing will happen. You only need to be concerned with the partial pressure of that. Remember, it's not able to see that, the gases don't see each other, so you won't even know that N2 was there. Okay? Letter D. The volume is increased, so that means you made it bigger. That means the gas is happy. It has a lot of room. So you're going to go to the side with more gas, more moles of gas. So that would be 2NO2, so you're going to the right. Okay, and E, the temperature is decreased. Well, it's going to depend. Is this system endothermic or exothermic? Okay, you look at delta H. Delta H here is positive, which means it is endothermic. Okay, which means heat is on the reactant side. So these are the two reactants, heat and N2O4. So if you decrease the temperature, that means you take this away, you're going to go to the left to fill it back up. So it's going to go to the left. Okay, pause the video and try this one. So it says, using the standard heat of formation in Appendix C, in your calendar I made a link for Appendix C, otherwise it's in your textbook. Find the standard enthalpy change for the reaction. So I have the Appendix C here. Here are the heats of formation. How much energy does it take to form that substance? N2 gas is 0 because it's already N2 gas naturally, so it didn't take any energy to form it. If you were to look up H2, it's also 0. It's right here on this side. H2 is also 0. Now ammonia gas is negative 46.19. That's the heat of formation of ammonia. So the heat of formation is 0 here, 0 here, and this is negative 46.19 kilojoules for every mole. Since there are 2 moles, I'm going to multiply that by 2. I'm going to get the heat of reaction here, delta H of RxN reaction, is equal to negative 92.38 kilojoules per mole of this reaction, okay? So this number tells me that it's negative, which means it is exothermic, which means heat was produced as a part of the product, 92.38. So I know it's hard to see, but you have 2 products, ammonia and 92.38. Those are your 2 products. Determine how the equilibrium constant for this reaction should change with temperature. Okay, so if you add heat, it's going to go to the left because you add on this side, it's going to go this way to consume it. So it's going to go left. If you go left, you're going to have less products. Since K equilibrium is equal to products over reactants, and this number goes down, that means K equilibrium will also go down. Okay? And if you remove the heat, that means you're taking this away. It's going to go to the right to fill it back up. So it's going to go right. If you go right, you're going to have more products. That means K equilibrium will go up or increase. Okay, lastly, how do you think catalysts affect K equilibrium? Well, K equilibrium is equal to products over reactants, right? Look at this drawing. This drawing shows you a reactant is A, reactant is B. The only thing that the catalyst change is the mechanism by which the reaction reacts, and also the energy of activation. So in the catalytic environment, you have the green line right here. The energy of activation goes down, but the energy within the reactants and products are the same, which means that the product is B over A. Since B is the same, A is the same, at equilibrium, the catalyst will not change K equilibrium. The value of KEQ is the same. Okay? The catalyst will increase the rate of both forward and reverse because the energy of activation changes. When one uses a catalyst, equilibrium is achieved faster, but the equilibrium composition is the same. You will still have the same number of A and B.